as was already said, I'm here to discuss ArcVR. This is the sort of framework that helps you develop sort of VR-based experiments and studies that you might encounter here at ARC. Talk will take maybe like 45 minutes, maybe a little bit longer, and at the end we're going to sort of I'm going to show how it looks like to actually build a sort of simple demo experiment with this. So as far as VR goes, there are very different types of VR that are used in research. You've got these sort of cave systems where you're projecting images on walls. You've got these sort of haptic suits, flight simulators. The type that I'm going to be sort of referencing today is the sort of more mainstream consumer grade VR that has sort of entered the market more recently. And these types of systems have sort of a small set of sort of key denominators. You'll usually see that they consist of like a set of controllers, one for each hand. The controllers have a series of actuators and haptic feedback. Typically, you've got the head-mounted display, which provides you with stereoscopic vision. So that's like one unique image for each eye. So you have actual depth perception. You have a set of headphones for audio and some kind of tech for spatial tracking. So whether that's sort of gyroscopes built into the other hardware or these kind of lighthouses or a combination of the two. Yeah, the sort of this setup is the sort of latest iteration in a long history of like progress done in the areas of like 3D rendering, photorealistic lighting, larger monitors, all of this tech, which is essentially meant to provide a higher level of immersion into virtual environments. This pursuit for more immersion has been primarily driven by the video games industry, but its fruits can now find like application in all kinds of fields, not least including research. And so if you think of immersion, you can define that differently. You can be very immersed into a book you're reading because the characters are relatable. That would be narrative immersion. VR strictly deals with spatial immersion. And spatial immersion you can think of as the synthetic stimulus of the body senses through the use of technology. And if you look at these sort of key components of VR hardware, they indeed correspond to the sort of senses of touch, of vision, of hearing, and of balance, so your vestibular sense. And senses of smell and taste are very neglected in this area. So if you're looking at VR in psychology, the sort of status quo is that research is quite sparse and there aren't a whole lot of publications, but as you can see here, sort of slowly picking up steam, especially now as sort of VR proliferates itself onto the consumer market and becomes more accessible. Your sort of average VR kit costs like a few €100. It's no longer the sort of highly specialized equipment that costs a fortune. And these are the sort of peer-reviewed articles in some database that are VR related and contain the one of the keywords: health, assessment, treatment, rehabilitation, recovery. This would be more like medicine as opposed to psychology, but most research areas do reflect a similar trend. And if we're looking at psychology specifically, you would find sort of two major camps. One is the sort of looking at the effects of VR itself. So how does it affect gaze, visual attention, these kinds of things. And the other camp is clinical psychology. So psychotherapy, treatment, and these are often about sort of using exposure therapy to help patients with disorders like PTSD and social anxiety and these sort of things. There are also some like buried treasures in behavioral psychology, which tends to be a bit closer to what we do at ARC. And many of these are related to proxemics. So proxemics is your interpersonal distance and positioning, where you stand relative to other people. And this is mainly because this publication down here is sort of one of the most cited ones on this whole domain, and many other publications sort of build on top of it or derive from it. For further reading, I'd recommend looking up Jim Blaskovich, who tends to be a sort of co-author or contributor in many of these and is a leading researcher in this area. So in all of these papers, the researchers either like voice their enthusiasm or indeed lament some kind of problem or feature with VR. to do this kind of research. And the underlying question is why bother? So why hassle with all the problems that come with it? What are the advantages, the reasons to use VR? When should we use it, and when should we not use it? And one of the sort of primary incentives to use VR is, of course, that the higher realism and the higher immersion can provide a stronger stimulus. So ecological validity is the measure of whether results of a study are applicable in real life situations. And the sort of traditional experiment tends to sort of lack that because they sort of reduce things to simple cognitive tasks. And it's not sure if the results are applicable in a real life situation where you have far more complex stimuli and essentially a limitless amount of response options. Another reason is that VR provides an unprecedented amount of experimental control. So if we wanted, for instance, to do a live study on, say, racial bias, we would have to like recruit different actors of different races, and that's like hard enough to do as it is. We also would have to ensure that their height, their age, and all these other characteristics roughly match so that we only have this one variable. In VR, you can obviously just take the same model and just change the skin tone on like a slider scale. So we have full precise control over this one variable, allowing you to leave everything else constant. And this is indeed something that was done in this study here. This is from 2008. So before any sort of consumer grade VR was really readily available. So you could probably make this look a little bit better than nowadays, but nevertheless, it did provide some interesting results. The sort of general idea I'm getting to here is that in a lab environment, you might have the most experimental control, but it generally lacks ecological validity. VR provides a sort of modest amount of both. While live studies might be very ecologically valid, you don't have control over all the like small deviations in the environment. While in VR, you can obviously make the environment whatever you want it. Not only can you make the environment whatever you want it, more importantly, you can keep it the same. So that gives us a reproducibility. There's a fair concern as to how reproducible certain psychology type studies are. With VR, the whole study is just a computer program. It's just an executable file. So researchers in Tokyo could be running the exact same setup as researchers in California or in Berlin. So provided that they have the same hardware and a computer to run it on. Additionally, there is a lot more like leeway in terms of safety and feasibility of a study. There's obviously a limit as to what we can do in a like a regular lab setting. Great example is this. This is a sort of VR study where participants had to like escape a sort of building, and there was a fire in the building, and then those participants could put themselves at risk to help someone who was sort of trapped with the fire approaching. This is obviously not something we can really do in like a real life study, or even if we could do it, it would be very expensive. But in VR, this is just perfectly fine. Furthermore, there is the sort of, in contrast to more traditional experiment apparatuses, navigating and interacting is more intuitive. So I can speak from personal experience from some of the experiments that I've done at ARC, that there is large discrepancies in how adept people are at controlling a character on a 2D screen with like a controller or a keyboard and mouse. And these discrepancies respectively affect the test results. And this is obviously because some people have prior experience with playing video games, or just have used the computer longer, or just have a talent for that. With VR, you sort of have a sort of interface that's adapted to the human body. So moving the mouse to look around a virtual environment can require getting used to, but all of us are already used to looking around using our head. Now you could point to the VR controllers and say that those have buttons, and those have to sort of be learned, but that's a fair concern, but these controllers tend to be designed in such a way that they are very intuitive to use. So these are the Valve Index controllers, and you can see they're sort of strapped to your hand, so you can freely open and close your palm, and sort of closing your palm would be equivalent of grabbing some object in virtual space. I've seen this described as being an empowering environment, as it empowers the participant to freely explore and experiment and just do what they're supposed to do, not requiring you to acquaint them on what the exact controls are. Last but not least, we also get inherently richer data from VR experiments than more traditional ones, since even the most rudimentary basic VR setup has a sort of budget version of motion capture built in, as we always know where the player's hands and their head is. And the sort of orientation of the head-mounted display also gives us a rough approximation of their gaze, especially since the field of view in virtual reality is more narrow than it is in real life. There's also 6 degrees of freedom of movement here, while sort of traditional first-person movement navigation systems only have 4. Needless to say, VR also comes with its own drawbacks and challenges. A big one of these is just one thing that we might have seen reflected in the studies I've shown so far is the sort of novelty of the whole tech. So it's really hard to decouple a VR-based experiment from a VR experiment. Many people haven't had any experience in VR at all, and their sort of wow effect or their disappointment might sort of give way to unintended side effects, like distractions to the novice user and these kinds of things. There's also a long list of technical constraints. So having worse depth perception, VR displays tend to actually have higher resolution than your average PC monitor, but because it is pressed right up to your face, it's sort of perceived as being lower resolution. And at long distances, you've got sort of worse depth perception that you have in reality, of course. On top of that, the rendering VR graphics is more performance heavy than regular graphics, and you've got some deployment constraints, as in you can almost certainly forget to run a VR experiment online, like a browser type experiment on. And you obviously have to provide participants enough space to move and such, so without bumping into walls. Then there's motion sickness. Motion sickness has been a problem with VR since its inception, and different people are differently susceptible to motion sickness. Some people can be in an intense VR simulation indefinitely, while others can have to take a break every few minutes. As far as development cost goes, not only are VR experiments generally require a bit more effort than your average 2D form-based experiment, it's also a more unique development process. As in, it comes with some unique problems. Take, for instance, the uncanny valley effect. If you've got a realistic 3D model of some human, but it's got a walking animation where they walk like a stiff robot or some cartoon character. If it's going to look really weird on a regular 2D screen, it's going to look even weirder in virtual reality. So it's always recommended to use motion tracked animations, which are smooth, and these of course have to be sourced from somewhere. There's also self-embodiment. So that's the fact that the user can't see their own body and their own hands in virtual space. There is evidence that this leads to worse performance in certain tasks, and also presence. So obviously no participant is fooled by VR. Everyone can distinguish the virtual world from the real world. But if the environment isn't interactive enough, you have a concern that there might be sort of audience effect, where the player sort of treats it more as watching a sort of 3D movie as opposed to actually being part of that virtual location. So one thing that helps with this, according to this study here, is to use so-called preambles. So a preamble is that before the experiment even starts, you place the participant into a sort of virtual recreation of the room that they are actually in. This sort of provides a smooth transition from the real world into the virtual world, and it supposedly helps with presence. Lastly, for challenges, we have the challenge of ethics. What are you willing to or allowed to expose participants to in such an immersive setting? 2 great examples is this one, where researchers built a sort of room 101 from 1984, where participants be subject to disturbing events like spiders crawling around or explosions or the floor vanishing underneath them, things like that. Another great example is this is a virtual recreation of the milligram experiments. So participants are administering sort of lethal electric shocks to virtual characters. And you can see the challenge here. So obviously, least that you can do is like make sure participants are sufficiently informed and that they consent to be put through whatever you want to put them through. In essence, so you should probably think carefully whether if an experiment actually benefits from VR. Definitely not all experiments need VR, and there are many situations in which that can be more of a hindrance than a help. But it obviously does come with its own upsides. Now, after this, after like looking at these pros and cons, I finally get to the actual meat of this talk, which is ArcVR. This is a library or framework to sort of make the development of these kinds of studies easier. And we'll look into how this sort of solves some of these challenges and problems that I've outlined before. ArcVR is built on the Unity engine. The choice of engine here is a bit of a no-brainer, as in this is the most highly used engine in VR research. Alternatives like Unreal Engine or Godot or whatever you hardly see them. And this mainly comes down to there being a sort of large library of pre-built assets and add-ons, which you can either buy or many of them are free. And this is particularly useful, I find, to researchers, as researchers tend to have a lower standard than video game developers when it comes to having a sort of coherent style or like artistic value. So if like 3D models or environments are made by different artists and they don't fit together perfectly, it's not a big deal for a psychology experiment. Additionally, the sort of threshold for actually creating an application is fairly low. You don't need a long history of experience to get something done. The learning curve is fairly forgiving. And nevertheless, it is a very powerful and flexible engine with a huge catalog of features. And one of these features is that it comes with its own built-in XR plugin management system. And this plugin management system is, in fact, the only dependency that ArcVR uses. So keeping the dependencies low does a couple of things for us. Firstly, it sort of keeps a good overview of what code is running, what are the possible performance bottlenecks. And also, if we want to update our project to a new Unity version or do some maintenance task, it's much simpler to do it, because this tends to get more painful the more like baggage you're dragging along, especially knowing how Unity likes to like deprecate and rework its sort of inner components. Depending on only one of those makes this whole thing more sustainable. So what plugin you plug into the XR plugin manager is up to you. So ArcVR doesn't care about that. And typically each sort of VR OEM tends to have their own separate plugin. So there'll be one for the Oculus Rift, there'll be one for Windows mixed reality and so forth. But to maximize compatibility, I personally recommend using OpenXR. OpenXR is a sort of standard that's maintained by the Kronos group. These are the same guys that do OpenGL and Vulkan and other stuff. And pretty much all VR headsets on the market really work with OpenXR or have at least expressed the intent to provide compatibility in the future. This makes ArcVR essentially hardware agnostic. So if you have a HTC Vive controller or a Valve Index controller or an Oculus Rift controller, from a software development side in ArcVR, this is just a controller. The manufacturer doesn't matter. Same goes for the head-mounted displays. ArcVR itself is divided into a series of packages. So there are 6 at the moment. Maybe there'll be more in the future. And all these packages are sort of dependent on this like core package. This is like the sort of primary interface with the exterior. And this provides a sort of modularity, as all these packages are agnostic to one another. They're all in separate assemblies. So the motion package doesn't know what's going on in the UI package and vice versa. And this modularity is intended to sort of be adaptive to the wildly varying specifications that you have from experiment to experiment. So some will only require certain features that others don't, and you can sort of pick and choose what you need without having to drag a whole lot of unnecessary stuff into your project. So these packages are sort of collections. So these down here, at least, are sort of collections of like the most like industry-wide solutions or practices to certain problems. And they sort of provide like sort of default pre-built objects that you can use, but these objects can also be modified and extended fairly easily in any way you want. So this whole thing is fairly adaptable and extendable. And it's sort of focused on prototyping. So from my own experience at ARC, most experiment specifications aren't exactly clear until at least the third prototype. So the idea here is to get those fundamental building blocks in place quickly, and then build, once you sort of know what works and what doesn't, you can build on top of that the more complex things later on. So it's to cut down on the duplicate work. So when you're building a new VR app, you're typically building the bottom layer again and again. And this should like help in the prototyping phase in particular. Now I want to take a brief look into each of these packages and see what sort of features and functionality they provide. We'll start with the core one. This sort of comes with the sort of essentials. You've got like, you can create basic player rigs. So that's like VR setups that involve the sort of head-mounted display and controllers. You can use the input of the controllers. There's also an integrated developers console. So that's a useful tool for the developer or the experimenter indeed to like modify or change something in the project on the fly last second after it's already been built. And you can also use this to like really run any code function that you want. Say for instance, you want to like start or pause or stop the experiment, but you don't want to like add sort of UI buttons because the participant might mess with them, or maybe you're just too lazy. So you can easily just put that in as a sort of console command. There's a sort of integrated setting system. So variables are, you can sort of save them externally into these JSON type files. And if you want to run the experiment on different parameters, all you have to do is just change those files without having to rebuild the whole experiment. And this also, you can use it for things like localization. So if you want your experiment to run in different languages, you can just have different settings for each language, write the translations in there and change the language. There's also logging tools because of obviously when we're doing experiments, we want to actually like log some data and some other utilities. And all of these components don't really like require writing any code to work, which is sort of an intended feature of this framework. So this package might be enough for a very basic experiment. For instance, when you want someone to cross a street in VR, you don't actually need anything else. But if we want to do something more complex, we get to the next to the other packages. ArcVR-Net is there to provide sort of networking multiplayer functionality. This is a bit of a special one in that it sort of actually does depend on an external package, and it sort of integrates the core package with Unity's netcode for game objects, or also known as ML API. And this is the sort of newest official networking solution for the Unity engine. So it enables all the other packages with sort of multiplayer functionality. There's also a player spawning system and some other stuff. Using just this package alone lets you do some simple things, as in this video, for instance. You see we've got a VR player here, and they're sort of being represented as a sort of capsule object to another player. And this is something that you can do fairly easily with this. If we combine the net package with some of the other packages, we can do something more sophisticated. This is an example where it's a sort of game where players can sort of harvest melons by like pointing their VR controller at them, and these melons will include rewards or not. And if there is a reward, it will launch a firework like there. And this is to like study social information and things. And this is how the player sort of looks to like the VR player looks to like a non-VR player who's playing for third-person perspective. And you can see, even though that the VR player is sort of teleporting around because this field is larger than the actual like space provided, it sort of looks like they are walking, or in this case more like running from one place to another. Speaking of walking and teleporting, we get to the motion package. This is all about navigation and movement. At some point you ran out of space in reality, and you need to provide some way of letting players sort of move around the virtual space without actually moving in reality. And the primary concern here is motion sickness. So the biggest factor that causes motion sickness is that if you move or rotate the player in the virtual world, but they are actually just standing still in reality, this creates an ocular vestibular mismatch. So your eyes are essentially reporting some kind of movement to your brain, which your sense of balance can't confirm. And this is while sort of using teleportation and frames of reference instead is a common solution. And players can sort of point out a location that they want to go to with their controller and then teleport towards there. And there's different providers here that have like different transitions. So you may want to like instantly teleport them there, or you may just want to like turn the screen to black, move them there, and then open the curtains again, so to speak. And this solution does tend to solve motion sickness, but it does come with some other problems, namely like orientation and spatial awareness. As I said, this sort of sense of depth in VR tends to fall off after some distance. So common recommendation is to use hints inside the player's FOV. So like some kind of landmark or some kind of object, and when you teleport towards it, the sort of size by which it increase helps the player to orient themselves as to where they just moved to. And the motion package uses this sort of virtual representation of your feet. These feet are sort of the orientation that your head has, and their size sort of indicates how far you are going to be teleporting. And this is the sort of example of a sort of landmark. And yeah, you also have some locomotion provider and turn provider. These are just like different kinds of movements that don't involve teleporting. And you can like pick whichever you want. Moving on, there's the avatar package. You saw this in this like video of this melon game. You can sort of represent a player through like a humanoid 3D model in the virtual world. And this is what this package does. It's sort of divided into a pose provider and a pose assumer. Essentially what this comes down to is that we have as input just the very limited information that we have is where is the left controller, where's the right controller, and where is the head mounted display. And based off of that, we need to like estimate or guess what pose is the player actually like making. So where is their head, hands, where are their feet, where's the torso, where's the neck, where are their elbows? And that's what the pose provider does. It takes these inputs and says, okay, the player's probably in this kind of pose. And then the pose assumer can sort of map any sort of humanoid 3D model to that pose. Now, as for the solution of this pose estimation, there is a whole like range of literature on its own and some very sophisticated methods, as in this this master's thesis here, temporal IK, which uses a sort of temporal neural network, so machine learning. And you can see here in red, that's the sort of estimated pose by the machine learning program, and in blue, that's the motion captured actual pose of the player. You can see these are fairly like decent results. What ArcVR uses is indeed not that, but something a lot more sort of a lot less sophisticated. And it essentially just narrows down the problem of being, is the player leaning or is the player crouching? And you can theoretically do all sorts of acrobatics in VR, but in most use cases, you're either going to be standing, crouching, or leaning. So narrowing it down to just these three makes the sort of underlying model a lot simpler and gives like better performance. But of course, as with anything ArcVR, you could also just replace this with your own more sophisticated model. So long as the inputs and the outputs are the same, what happens in here is up to you. There is just this default object that indeed just uses sort of numerical values to estimate that the player is leaning or crouching. So another thing that's very useful from having this division between provider and assumer is that we can have multiple pose assumers that all take their data from the same pose provider. So we could have like, we could have like a mirror image of yourself in front of you, but we could also have multiple mirror images of one person sort of surrounding the player. Or we can indeed like change the size of them. So you could have like a giant version of yourself, or indeed the opposite, a sort of tiny version of yourself. Moving on to the last two packages, I'll try to keep this sort of brief. The UI package is about UI interaction. Obviously, it gives a sort of laser pointer which you can like press buttons and select toggles. So you could, for instance, have the participant fill out a form within the experiment itself. You can also like move these UI canvases or anchor them to different things. You could, for instance, have it like attached to the player's controller. There's a funny thing that happens here is that players will sort of hold the laser pointer perfectly still and then move the canvas into it, which is essentially like the inverse of what a laser pointer and a canvas is supposed to be, but it's more precise that way as the pointer has sort of leverage. Either way, I digress. The UI package also comes with like default elements as well as sort of UI variable links. So you can essentially like link a sort of UI element, some kind of text, or like a drop down or some number on a UI element to some variable in some code. So when you change the variable in the code, the change will be reflected on the text, and vice versa as well. When you change the text, the variable will change. So this is like an easy way of making like an options screen or something. Then for the last one, ArcVR Physics, this is about physical interaction. So picking things up, tossing them, knocking them over. And there are a range of like different grabbable object types here. So you may want the player's hand to like interact with like some ledges or a wall, but you don't want the player to pick up the whole building. This is, you have sort of different types for sort of different expected behavior. So you can like differentiate between like heavy furniture or a small like tin can or something. And the key challenge here is how do you represent a physical constraint without that physical constraint actually being there. So it uses like a combination of haptic feedback as well as like some other techniques, which I won't go into too much detail because that takes too much time. But you can sort of set if an object is supposed to be heavy or light or completely static. Here's a sort of short video that sort of showcases what you can do. So you can like knock things over, you can pick them up, you can sort them, move them to different places. You've got these sort of virtual hands, the fingers adapt themselves to the like surface of the object, not always perfectly, but well enough. And you also have like different sort of physics interaction providers. So if you don't want these hands, if you want like a more simpler version of them where it's just the controller and you grab objects by their center, then that's another option you have. Then that actually concludes my sort of overview of ArcVR. I'd like to show you two sort of very simple demo scenes. These are sort of very simple demos that with this library you can put together in an hour or less without like really having to write any code at all. After I've shown you these two, we can actually make such a demo ourselves. Let me just bring these up. So this first one is essentially a sort of playground. So this is actually something that would work with multiplayer. So if I had another player here, they could like join me in this room. So I'm in like this kind of like playground room, and I've got two hands, and I can like move over here and pick up this like basketball and bounce it around, and I can try to hit the ring or fail miserably at it. I can move over here and like knock over this pyramid. Or there is also a giant chess set, which I can like move the pieces off and play with another player theoretically. And you can see the hand adapting itself to the surface is not always perfect, but it sort of generally does the job all right. And over in this corner, there's a sort of security camera which sort of shows how I look to other players. So there's this same robot that you've seen in the other videos sort of mapped to myself. I can wave towards the camera and this kind of stuff. So that is sort of it for this first demo. This second one is similarly simple. It's a sort of simple game where I draw like sort of small spheres from an urn. I'm in this sort of room with the ArcVR logo, and it will tell me instructions that to click start with begin. My left controller is a sort of laser pointer, so I can click on start, and it will tell me to guess what color I will draw from this urn. So I can guess red, then reach my hand into it and draw a red sphere. So I was indeed correct. It will tell me as much. And the process will repeat. So I'll guess red again and draw red again. So clearly I'm the best at this game, and I do not need to go through the other 10 trials that this is sort of set up. Okay, so moving on, as I said, I would like to just like show how this now looks from the perspective of the developer. So how easy is this to use? And how much does it take to really like set up a basic experiment? So we're going to be building a simple demo like this sort of here. And the specification and idea for this experiment is something suggested to me by Ralph Kurvers. We're going to be looking into collective influence in non-compliance and nature conservation. The core questions here are: how likely is a person to break a rule when they watch others engage in rule breaking? And how does the number of rule breakers influence an observer's probability to copy this behavior? So the experiment looks like this. There is a sort of shore, there is like a beach with some water, and the participants is on the beach, and he's told to go and fish as many and catch as many fish as he can. And the beach is sort of divided into two areas. One is a sort of legal fishing area, and one is a sort of area that'll be marked as no fishing is allowed here. But there will be more fish to catch in the illegal zone. So there'll be a bunch of other people fishing, and the question is to see where the participants sort of go. So we're keeping up with the sort of proxemics thing from other VR studies, and seeing how does the participant position themselves relative to other players, and are they more likely to break the rules and go to the illegal fishing zone if there are more people here. Now, keep in mind, I'm planning on building this in the next like 10 minutes. So we're going to oversimplify things fairly dramatically. And these aren't going to be actually other players. These are just going to be like statues standing there. And this isn't going to be a multiplayer thing because I couldn't really like showcase that either. Before I forget, these are the references. These are like the other sort of publications that I referenced, and some more further reading. And that brings us to our fishing game. So this is a completely empty sort of fresh Unity scene. The only thing that's happened here is I've imported some like 3D models that I'm going to be using here. I've sort of prepared them a little bit. And I've already taken the liberty to import the Arc VR sort of packages that I'm going to be using. So you can see I've got the core package, not the avatar package, motion, physics, UI, and not the networking package because it's not a multiplayer thing. A sort of default scene comes with the main camera and a directional light. The directional light will serve as like our sunlight. Main camera I can just get rid of because we don't need that. And we want to like set up the environment. We want some kind of beach. I've got this terrain that's prepared, and at the moment it looks a little bit more like a desert. So we need some water. I'll just make a new 3D object, which is going to be a plane, and make it somewhat larger. Make it have a sort of water material, layer to water. And now we've got like our basic sort of shoreline or beach. And now we need to cut this thing in two. So to make an legal and an illegal fishing zone, I've got this kind of sign here, which if I turn it around, you will see it says no fishing beyond this line. We'll place it right in the middle, and maybe we can make a second one and place it further inland. Make sure that it isn't stuck in the ground. There we go. And since it says no fishing beyond this line, may as well add a sort of line to the ground. So I've got this dotted line thing, which we'll just move back here and put in the center. There we go. And that's our sort of division of legal and illegal fishing zone. We haven't really done anything with ArcVR so far. This is just regular Unity stuff. Now we want to actually have a sort of VR setup in here. Creating one is fairly simple. Let me just simplify all this so we don't have that much to look at. We simply select this AVR thing here, and we can create a player rig object, and that's it. There's a player rig. It's in the water here now. I'll move it to a more sensible location, like right there. And now I can already like move within room scale in this environment. Like if I click play, you can see that I'll have to compile it briefly. Like if I move this headset over here, like it will reflect that thing respectively, the movement respectively. So we want to go a bit further than this. And we also want our two controllers here. So I can select the player rig and click on add module, and it will give me the sort of checklist. There's not many options here. There's only left and right controller, which we want both. But if I had other packages in here, for instance, the avatar package, adding a sort of pose provider to this would be another option. So if I hit update, you can see now my player rig has three child objects. One is the camera offset that represents the head mounted display, left-hand controller and right-hand controller that represent the two controllers. And my intention here is to have the left-hand controller for like moving around, for teleporting, because this beach is bigger than my room here. So we'll have to allow some kind of movement. And the right-hand controller will be for holding the fishing rod. So I can do the same as I did with the player rig. I can select the controller and click on add module. And now I have a lot more options. You can think of this like some kind of sci-fi gauntlet, and you can choose which like weapons or modules or something to have on it. So for the left-hand controller, I want some kind of controller visual, so I can see my own controller in virtual space. I can select different ones here. I'll just go with the default Vive controller. And I want a movement provider. Now you'll see the movement provider will tell me it needs an input manager. So I'll just have to select that as well. Input manager essentially just lets me use the buttons on the controller. So this is what I was talking about in terms of it now creates a series of like default objects, and these will just work right out of the box. But I can also like modify and change them depending on what I need. So for instance, in this specific case, we want the player to only be able to teleport or move on the beach and not the water, because it's a fishing game, it's not a Jesus simulator. So we would sort of select this movement provider, and we see it comes with a movement restrictor. So this restricts what you can move on and what not. And I can create a new one of those by going to ArcVR motion movement restrictor. And here I can now set this sort of like limits or options that I want. So I'm going to just like limit teleport location by layer and let the player default teleport to everything except water. And there we go. So this is done. Then I simply drag the, select the movement provider and set this movement restrictor to be so override the default one. I can also obviously change whatever else I want. I could change the teleport mode to dash. I can change the sort of geometric shape of the ray or the color, things like this. But that'll be enough for movement for us for this purpose anyway. Moving on to the right-hand controller, this is what we want to grab the fishing rod with. Likewise here, I'm going to click add module. We're going to want a grab provider that also needs an input manager. We're just going to go with the most complex one, and we're going to add a hand interactor. That's the hand that I showed that like adapts itself to the surface. So there we go. So do we want to change anything with these default objects? Well, one thing that I can think of is we probably don't want the player to be able to let go of the fishing rod after they grab it, because that could lead to sort of problems like they leave the fishing rod on the shore and move somewhere else themselves or something. So I'm going to select the grab provider, And there are these sort of grab and release events. So these are essentially the buttons on the controller that I click to either grab or release an object. And I'm simply going to set the release event to always false. So once a player grabs an object, they can never let go of it. So now where we can grab things, we need a fishing rod. I've got this 3D model of like a bamboo fishing rod prepared. And in order, it's just a 3D model with some colliders. In order to make it actually like physically interactable, in order to make it grabbable, it needs a rigid body. This is just a sort of unity object for sort of gravity and physics. And then in order to actually make it work with the grab provider, it needs an AVR grabbable object. And now I can select the object type. So we've got heavy objects, light props, medium props. We'll just go with generic. And there you go. Now we could like grab and hold on to this fishing rod. Now, unfortunately, we can't get away without writing any sort of code for this experiment, because we need to. I need to somehow set like what when the player is fishing, when they are in the illegal zone, and when they are in the legal zone. So in order not to waste any time, I sort of prepared this fishing rod script. Let me just move it up. And I can show you the code right here. It's very simple. It's just these lines. And it's just a sort of integer that keeps track of the score. So this is how many fish we've caught. There's a Boolean which says is fishing. And this might look like a little bit of wizardry, but this is essentially, it just checks, is the tip of the fishing rod above water? So is underneath the tip, is there water or is there sand? If there is water, the player is fishing. And then illegal simply looks at the player rig and it looks at the feet. And if the Z coordinate of the feet is bigger than 0, we are fishing illegally. Otherwise, we are in the legal zone. So if you look at this line is at Z equals 0. So if we are to the left here, then we're illegal. If we're to the right, we are doing fine. And then this is just a function that runs every second. And every second, if the player is fishing, we add something to the score. And if the player is fishing illegally, we will add +3 to the score. If the player is fishing legally, we would add +1. So we'll fish 3 times as fast illegally. Fishing rod that we can grab. One sort of thing that we sort of want is for the player to now be able to see their score, right? We want to sort of, we've got the score in this code here, but it's just in the code. We want the player to see it. So I want like a sort of UI attached to the fishing rod that shows like how many fish they've caught. I can like use the dev console here to look for prefabs UI window. So this will give me, this will sort of set my search down here to UI prefabs that include the term window. There's 3 different ones. I'll just like pick this borderless one. I don't want something that's like this big. I just want like a small number attached to the fishing rod. So I'll just change the size to like 20 by 20. So it's a small square now. And we'll add a number. So new UI text. It'll be a 0. We'll center it and we'll turn it white. And there we go. So now this is just a text with a 0 on it. But what we want to do is we want to link this to this variable here on our fishing rod. So that's where these like UI links come in that I sort of mentioned in my presentation. So I can add the UI link text and say, okay, what do you want this text to actually reflect, which variable? And I can just drag the fishing rod into the target, show available fields, and it will show like all these variables that I have here. So it will show is fishing illegal, some other stuff that comes from inheritance through AVR component. And namely down here in public fields, it'll say score. Click on that, that's done. This will now reflect the score that I have. Now, I don't want this to be on the ground here, so I'm going to like parent it to the fishing rod and sort of set the position to sort of move it up like over here. And maybe have it like look at the player. There we go. Now, sort of only thing that we have left is to add some other like people or players in here. I've got this fake player prefab object, and I'll just like scatter these arbitrarily. You would typically have like different arrangements or have this randomized, but I'll just have like a group of legal fishermen like over here, and then like a small group of mischieving illegal poachers over here. Can simplify this a little bit by just adding everything to the plane. There we go. And that is it, I believe. Actually, one thing that we may still want to do is we want to log some data, right? So what's the point of doing an experiment without logging something? So I can use this AVR logger that's in the core package. I want to like save it to a CSV file. We'll save it with like a fixed delta. And now I can like add columns here. So first column would obviously be like a timestamp, call this time. Then what do we want to sort of log here? Well, maybe we want the position of the player, the position of their feet, like so position. And I can click on the player rig here, and it's got these buttons here. This one will bring up the documentation of the player rig, and I can search in here, and I will find that there is a property that's called feet in world space. So that's the position on the ground directly underneath the camera. So that's probably what I want to log. So in the logger, I can just drag the player rig in here and write the name of the property or field in here. So feet in world space. What else do we want? We might want the score. So I'll take the fishing rod here. Then I need the name of the property, which I've named score. So score, not without an I, and we'll name the column score. And maybe we still want whether if the player is fishing and if the player is illegally fishing. So all I'm doing is I've just like selected these three variables to log alongside position. So I'll just call this fishing and illegal. And there we go. Now I should be able to play this. Might need a moment to compile. No, this looks good. And I'll just get it in, take the controllers. And now I'm here on the beach that we just constructed. I've got the controller in my left hand and a sort of hand in my right hand. I can sort of teleport around, and I can not go onto the water. So as it was intended. So I can use my right hand here to grab onto the fishing rod. I can't let go of it anymore. This is just me holding it now forever. And let's go catch some fish. So I can like stand here on the shore, and there we go. You can see I'm catching one fish every second. If I now instead move back to the illegal zone, I will be catching fish much quicker, so 3 a second. So going back over here, that's 1, and that's 3. And yeah, these people are just like statues, but the idea would be to see whether if they incentivize me to break the rules more or less. So maybe we want to look at the data that this is now logged. So this is just, I can go into the logs folder and show sample.csv. That's where I told it to log, and it does have these like 5 columns. And if I want to, for instance, like plot out my score, you can see this sort of steep increase is when I was in the illegal zone, and this sort of small slope is when I was obviously fishing legally, and things like that.